Hello team, welcome to our week 7 video where we'll be discussing drainage and surface water on the golf course. Recall from our previous two videos on irrigation that heavy precipitation over a short period of time is more likely to run off the surface than it is to penetrate the root zone. This is demonstrated by this picture draining a bunker into a fairway. So a large volume is applied all at once and that water will move along the elevation gradient. This water will eventually come to rest in low elevation areas in, in order to quickly and efficiently move water out of the low elevation areas and prevent pooling and turf stress. Subsurface drainage is needed. Here is an example of a drainage dilemma that we remedied over the winter. This is a diagram of number 17 Champion Polymer Metal T complex. You see how water has the potential to accumulate between the two tee boxes, where after a heavy precipitation, the back half of number 17 polymer metal remains saturated for extended periods of time. This ultimately limits the number of available tee positions and also puts the turf in this area under increased abiotic stress. And we're going to get into more impacts of overly saturated turf when we start talking about turfgrass disease, but for now, we'll just limit this to abiotic stress from saturated conditions. So we need to install some type of mechanism to remove excess water from this area. And this was the solution. A herringbone style drainage system was installed under number 17's polymer metal tee box. A herringbone system features several laterals branching off a main line. The laterals are traditionally angled 45 degrees off of the main line using a Y coupling. If you're ever ordering these products, Y is usually spelled W-Y-E. Might be hard to find if you don't know that. Um, and then the trenches for the laterals and mainline will be graded using a tool called a dumpy level. There's a couple other names that all do the same thing, but it's used to verify an elevation gradient moving the water to a desired area. Here's a closer look at the construction in the trench. So 4-inch ADS perforated pipe will be encased in pea gravel. The pea gravel and the perforations allow water to enter the pipe and move away. You want at least 4 inches of pea gravel covering the bottom of the trench and another 4 inches burying the ADS pipe. While adding the base layer of pea gravel, it's important to maintain proper grading. You don't want to accidentally raise up a portion of the trench, inhibiting drainage. Another consideration is to ensure that the entire construction is below your average aerification depth. You wouldn't want a Procore ripping out all of your hard work. Once the infrastructure has been installed, it is time to backfill the drainage trenches. We will discuss all the benefits of aerification later in the program, but for now, know that improved drainage is a byproduct of aerification. So the subsurface around the trenches was core aerified repeatedly until enough material was extracted to fill the drainage trenches. And then once the trenches are filled and packed down, the final step is to resod the tee box with new drainage infrastructure underneath. I'm going to wrap up this video talking about water movement at Laurel Creek and how we can go about monitoring our surface water. This is all the surface water movement at Laurel Creek. Our plan is to sample from 6 locations. Those 6 include the upstream and downstream locations of the unnamed tributary. So this is by number 14 green and number 2T. This will provide some data on water entering and exiting the property. Next, the water body that runs underneath the clubhouse bridge is called Parker's Creek. and there's a discharge off of number 18 that eventually reaches Parker's Creek, so we are going to sample from that discharge area, and this is going to be an indication of the water quality leaving the property as well. And we have 3 additional spots around the golf course. So location A is between 9 and 18. This is an area that's surrounded by the golf course completely with the buffer zone of vegetation. So this will be a good indication of uh, the water quality when a body is surrounded completely by the golf course. Sampling site B is off of number 5T, and this receives runoff from both the neighborhood and the golf course, so this will be a good sampling site to see how the golf course and the neighborhood can impact the surface water. And then position C is removed from areas that receive plant protection products. Typically, there's still, of course, a buffer zone around them, but this location I expect limited inputs from golf course management practices. So looking at all of this as a big picture, I don't believe it's appropriate to even hypothesize what the water quality sampling will reveal. Uh, the most important thing that we can do right now is just create a baseline of data, and I wouldn't expect to see anything worth reviewing at least for a few years of after starting sampling, because you for a system this complex with so many inputs, you need a lot more numbers than we have. So the important thing is that we're going to monitor and keep tabs on anything that does start to look a little fishy. Attached in this week's email is an excerpt from a guide to environmental stewardship that has some additional information on the parameters of the water quality assessment, but I'm just going to highlight a couple of the biggest points with respect to those parameters. So here are the parameters that we're going to be recording for our water testing. Temperature, it's important to record temperature at sampling and during testing because the other parameters are temperature dependent in most cases, so temperature has to be considered in your analysis. Uh, Obviously, too high or too low, both extremes can cause fish kills, so temperature is an important variable. Dissolved oxygen, like I said, temperature related, so you expect dissolved oxygen higher at lower temperatures, dissolved oxygen typically lower at high temperatures. The acceptable range is 6.0 to 13.0 milligrams per liter. In anaerobic conditions, that can lead to fish kills and uh, anaerobic decomposition, which leads to some unpleasant smells. Another parameter is pH. The pH outside the acceptable range of 6.5 to 8.5 has the potential to disrupt natural chemical reactions. Conductivity is directly related to the amount of mineral salts present. In irrigation ponds, increased levels can cause excessive corrosion on equipment. So if increased conductivity is having that effect on equipment, imagine what it will have on the aquatic life. And then we wrap up with nutrients, nitrogen and phosphorus. So the most likely cause of increased levels of these is fertilizer applications. Um, Typically in aquatic settings, nitrogen and phosphorus are limiting nutrients, so they keep the population of certain organisms in check. But when they are abundant, you get algal blooms and other uh, adverse effects in your water body. So we're going to be testing these and keeping an eye on our surface water at Laurel Creek. So that will wrap up week 7's video, and let's have a great week.